Welcome to this explainer on process control. Look, if you've been staring at textbooks filled with Laplace transforms and endless Greek letters, just wondering how any of it actually applies to a real physical chemical plant, you are definitely in the right place. Today, we're going to bridge that gap between abstract engineering math and real-world physical systems. We're going to decode these equations and show you exactly how physical systems behave.
All right, let's quickly run through our syllabus for today so you know exactly what to expect. First up, predicting process system behavior. 2. First-order systems explained. 3. Real-world first-order examples. 4. Second-order systems explained. And finally, number 5, real-world second-order examples.
Okay, let's jump right into Section 1, predicting process system behavior. So, the absolute fundamental goal of process control is predicting dynamic behavior. Skipping the heavy academic fluff for a second, what this really boils down to is just needing to know how physical systems change over time. Think about it. If you open a valve, exactly how fast does the tank fill? Or if you crank up a heater, how quickly does the temperature actually rise? In engineering, we try to predict how an output variable responds to an input forcing function using linear differential equations, and that right there is our baseline. Moving right along to Section 2, First-Order Systems Explained. Let's start with the baseline of our concept to reality pendulum. Now, in a lot of your textbooks, you're going to see this referred to as a first-order lag, or maybe a single exponential stage. But the absolute crucial point for any first-order system is this standard Laplace form. The output variable y of s over the input forcing function x of s equals the steady-state gain, Kp, divided by the time constant tau times s plus 1. Any physical system that fits this exact mathematical model is officially a first-order system. The real giveaway? Notice that the denominator must be in the form of tau times s plus 1. Okay, here is a quick study hack. I'm going to break down the two key variables you absolutely need to memorize for your exams: gain and the time constant, or tau. So gain, represented by Kp, is your steady-state conversion factor. It basically just tells you how much the output changes for a given change in the input, once everything completely settles down. On the flip side, the time constant, tau, dictates the actual speed of the system response. A small tau means the system reacts super quickly, while a large tau means it's really sluggish. Now, what's genuinely fascinating is how a first-order system reacts when you suddenly change the input. We call this a step response. It doesn't just instantly snap to the new value. No, it follows a single exponential lag. But here is the most important exam trick you can take away from this. If you introduce a step change, the process response is exactly 63.2% complete when the elapsed time perfectly equals the time constant, tau. Furthermore, if that response just continued at its initial rate of change, it would actually hit its final ultimate value exactly at time equals tau. Pretty cool, right? All right, Section 3, real-world first-order examples. Math is great and all, but let's ground this in physical reality so it isn't just a bunch of random Greek letters floating on a page. Like, what does a first-order system actually look like in real life? Well, a thermometer warming up in a fluid bath is a perfect, totally intuitive first-order analogy. If you plunge a cold thermometer straight into hot water, the mercury inside doesn't instantly snap to the new temperature. It rises really quickly at first, and then it kind of slows down as it approaches the bath's temperature. That right there, that's your single exponential lag. And this behaves exactly like a single open tank filling up with liquid to a new steady-state level when you bump up the inlet flow. Both of these physical situations fit that exact same math model we just covered. Now, to derive the transfer functions for these real-world examples in your coursework, you are always going to follow these exact 3 steps. Seriously, consider this your derivation cheat code. Step 1, write a transient mass or energy balance. Basically, accumulation equals in minus out. Step 2, introduce deviation variables. This gets rid of your steady-state initial conditions, which cleans things up nicely. And Step 3, apply the Laplace transform to turn your messy differential equation into simple, clean algebra. Master this 3-step process, and you can model literally any first-order system. But what happens when we start connecting multiple tanks together? Or what about when the fluid itself is so heavy that it has its own momentum and inertia? Well, that simple first-order model, it completely stops working. And that transition question propels us right into Section 4, Second-Order Systems Explained. Welcome to second-order dynamics, also known as quadratic lags. We're leveling up the complexity here by introducing a second-order differential equation. Instead of just having one parameter to characterize the dynamics, we actually need two now. Tau, which is the natural period of oscillation, and a brand new variable called zeta. And looking at the math brilliantly illustrates the core difference. Notice how the denominator completely changes here. We've gone from a simple, linear tau(s + 1) to throwing in a full quadratic lag. We now have an s² term, and we've introduced zeta, which is known as the damping coefficient. The addition of this damping factor fundamentally alters how the physical system is going to react to any disruptions. According to the process literature on this, systems with second-order dynamics respond drastically differently to inputs than simple first-order systems ever could. When an output changes under the influence of an input, it no longer just smoothly and calmly approaches a new baseline. Nope. The presence of that s² term and the new damping factor means the system can exhibit really complex, higher-order dynamics. So the magnitude of zeta, that damping coefficient, entirely determines the actual shape of the response. The best way to think of it is like a car's suspension. If zeta is less than 1, it's considered underdamped. It's like a bouncy lowrider. It's going to overshoot the target and oscillate back and forth before finally settling down. Now, if zeta is exactly 1, it's critically damped. Think of this like a perfectly tuned sports car that reaches the target instantly without overshooting at all. And if zeta is greater than 1, it's overdamped. That's like driving an old truck through thick mud, resulting in this really sluggish, S-shaped curve that just slowly crawls to its final value. Let's move to Section 5, Real-World Second-Order Examples. Let's swing the pendulum back to reality and see where these different zeta values actually play out in a real chemical plant. Interestingly enough, inherently second-order behavior actually arises rather rarely in the pure physical world of chemical processing. While mechanical engineers are out there dealing with second-order spring mass systems all day long, chemical engineers usually have to create second-order systems through specific, intentional combinations of equipment. The literature points out three main ways these second-order systems form. First, through multi-capacity processes, like hooking up two first-order systems in series. Second, through inherently second-order systems, meaning they possess actual physical mass and inertia. And third, by simply slapping a controller onto a standard first-order unit. Let's actually look at a couple of these right now. Okay, so if you connect two interacting tanks, meaning the flow between them physically depends on the fluid levels in both tanks at the same time, they form a multi-capacity system. Because they interact with each other, they create a cross-product term in the denominator of our transfer function. This creates massive mathematical resistance that heavily slows down the response. As a result, interacting tanks will absolutely always give you an overdamped response. Because zeta is greater than 1, it's going to be very, very sluggish. Alternatively, consider fluid oscillating in a manometer U-tube. Because that actual column of liquid has real physical mass, it inherently possesses inertia. When the pressure changes, the liquid accelerates, completely overshoots the equilibrium point, and physically bounces back and forth in the tube. This makes it an inherently second-order system driven by those unbalanced pressure forces. Unlike those interacting tanks we just talked about, the manometer can actually be underdamped, giving you that bouncy, oscillatory response where zeta is less than 1. I'm going to leave you with this final, somewhat provocative thought. The vast majority of second-order dynamics you will ever encounter in the field occurs simply because a control system was installed on a basic first-order process. If merely adding a controller fundamentally changes a system's underlying math from a smooth exponential curve to one that can potentially bounce, oscillate, and completely overshoot, how will you approach your next plant design? Keep that in mind as you study for your exams. Thanks for hanging out with me on this explainer, and I will definitely catch you in the next one.